Today we will find the solution of second order differential equation of the particle moving under inverse square force. It is also called orbits in an inverse square force field. So, this article may be written as orbits in inverse square force field, and it may also be called as solution of second order differential equation, which we have derived in the yesterday lecture. So, what is that second order differential equation? We know that that equation is d square u upon d theta square plus u is equal to minus mu upon L square u square f of 1 by u. This is our second order differential equation. That is d square u upon d theta square plus u is equal to minus mu upon L square u square into f of 1 by u. Now, for solving this equation, we will use this force as inverse square force, since the force is inverse square force, So, this force may be written as 1 by r square, that is inverse square, or it is equal to minus k by r square. What is minus? What is significance of minus sign? This minus sign shows the force of attraction and plus sign shows the force of repulsion, or this may be written as minus k into u square, because 1 by r is equal to u. So, F of 1 by u, that is force, is equal to minus k u square. This is second equation. So, we will put the value of force F 1 by u is equal to minus k u square here. Then we will get d square u upon d theta square plus u is equal to minus mu upon L square u square into minus k u square, or on simplification this u square will cancel out and minus into minus plus, and we will get this equation as d square u upon d theta square plus u is equal to mu k over L square, mu k over L square. This is equation number 3rd. So, this is simple equation. Now, we will reduce this equation as simple harmonic motion equation. You know that equation of SHM is d square x upon dt square plus x is equal to 0. You know that this is called equation of SHM or simple harmonic motion equation. So, take this term from right hand side to left hand side, you will get d square u upon d theta square plus u minus mu k over L square is equal to 0, and putting both these terms, put u minus mu k over L square is equal to x. Let x be the another variable instead of u. So, this term, I am putting this term as x. Now, we will reduce this u also in terms of x. So, taking derivative of this equation on both sides, we will get du over d theta minus 0 is equal to dx by d theta. Is it clear? Because use variable, x is variable, but these are constants. So when we take the derivative of this equation, we will get this du upon d theta minus this constant is 0, derivative of constant is 0 is equal to dx by d theta, or d square u upon d theta square. Taking another derivative, we will get d square x upon d theta square. So simply we will replace this d square u upon d theta square as d square x upon d theta square. So this equation become d square x upon d theta square plus this is x is equal to 0. So this is become this it will become equation of simple harmonic motion. This is SHM equation. We know the solution of this equation because it is harmonic equation and we know its solution. We know its solution. We have already studied this SHM in lower classes, that is 10 plus 1 I think. So the solution of this equation is x is equal to any constant into cos of theta minus theta naught. So this is standard solution of this equation. Cos. Why cos? Because cos is harmonic function and this equation is also harmonic equation. Now put the value of x in this solution. So what is x? X is u minus I have written in the previous part, that is x is equal to u minus k mu upon L square. K mu upon L square. This is x. I put this value. So this x is u minus k mu upon L square is equal to a cos theta minus theta naught. So this equation again becomes in terms of u and theta. So again put the value of this u as 1 by r, because we have put this value u is 1 by r only for simplicity or only for convenience, but we got the final solution. Now again reduce this equation in terms of r. So this u may be written as 1 by r minus k mu upon L square, this is mu, and is equal to a cos theta minus theta naught. Now further it may be written as 1 by r is equal to, take this equation, this term on right hand side, I will get k positive mu over L square plus a cos theta minus theta naught. So it will become positive on right hand side. Now we will reduce this equation as equation of conic. So what is the equation of conic? We know that equation of conic is 1 by r is equal to 1 by L into 1 plus e cos theta minus theta naught. So I have written this equation in the previous lecture. This is equation of conic. So we will reduce this equation, or we may write this equation as the equation of conic. So how we will get this equation? This equation may be written as 1 by r is equal to, take this term as common because we need 1 as the first term. So on taking common, k mu upon L square is common, 1 plus, because it will become 1 plus and a into L square over k mu into cos theta minus theta naught. So put this term as 1 by L, or compare this equation with standard equation of conic. So compare this equation with the equation of conic, that is 1 by r is 1 by r. This one will become 1 by L into 1 plus, and this is E into cos theta minus theta naught. So, what is L, what is E? So, where this L, 1 by L is this, and L is L square over mu k. It is 1 by L, and we will take its reciprocal, then L is L square by mu k, and eccentricity E is this, that is E L square over k mu. So, these are the constants. This is called semi-lattice rectum. It is semi-lattice rectum, and it is called eccentricity. So, these are the terms used in conic. So, on the values of eccentricity, we may write this equation as E is more than 1, E is equal to 1, E is less than 1, and E is 0. This is constant E. So, for 1 it is hyperbola, for equal to 1 it is parabola, and is less than 1 it is an ellipse, and more, equal to 0 it is equation of circle. So, there are 4 possibilities of the eccentricity or equations. So, the solution which we have discussed from the solution of the second order equation, the solutions are of 4 types, means there are 4 types of different paths which may be followed by the particle moving under inverse square force, and these paths may be derived in figure. This one is circle, and second one is ellipse, this ellipse second, first, second, and third one, this is parabola, and it may be parabola. So, I am drawing these figures from common point, this common point O, and last one is hyperbola, that is this one is this one and this one, hyperbola, fourth one, third and fourth. So, there are 4 different types of paths which are followed by the particle moving under inverse square force. So, this is the exact solution, or this may be called as the equation of orbit. So, they are basically, these are orbits in which particle is moving. Particle may be moving in the circle, in an ellipse, in parabola, or in hyperbola. So, it will follow one of the path out of these 4. Now, we know that when there is a curved path, particle is moving in a curved path, then there must be a turning point, because when you draw a circle, then there is a turning point. In case of parabola, again there is turning point. In case of hyperbola, in case of ellipse, in all cases of curved path, there are turning points. So, what are turning points? Turning points. Turning point means the points from where the particle turn, and we know that when body turns, when particle is moving from here to this point A to B, and then it will come back from B to A, then at turning point the velocity becomes 0. So, turning point is that point mathematically where velocity is 0. Velocity 0, that is r dot is 0. If r dot is 0, then its kinetic energy, which is half mu r dot square, it will become 0. So, 0 into something 0. So, when kinetic energy or half mu r dot square becomes 0, this is the condition for turning points. So, in conic, in curved path, there must be a turning point, either 1 or 2 or more than 2. These are turning points. So, we will discuss these turning points in detail in the next lecture. Thank you very much.